Graphing polar coordinates often seems more complicated than graphing things from the Cartesian plane, but the only difference between graphing polar equations and graphing rectangular equations is that they're just more weird looking, that's all. It's exactly the same. The way I learned to graph things in the coordinate plane, I can use exactly the same methods to graph things in the polar coordinate field. So what I normally do is I plot points. And in order to save myself time, what I'll ordinarily do is test for symmetry. Now, I'm not really going to spend a whole lot of time on this because this is really only useful for like post-apocalyptic worlds and things like that. Because most of the time, unless there's no power and there's just chaos everywhere, there are going to be computers and stuff like that I can just use. So what I'll do is I'll just put my polar coordinates into a calculator or a computer, and I'll just use that, and I won't spend kind of like my time like a caveman, just like drawing crap on a wall or whatever. So what I'm just going to do is put this in here just in case there is some kind of catastrophe and there is some kind of like end to the world and I can't use my calculator, so I've got to be a caveman and just draw this thing. So what I'm going to do is kind of just go over, plotting points, that's exactly the same. I put in my R, I put in a theta and I get an R. It's actually the opposite way around. So I've got points, R theta, put in my theta, I get an R, I got a point. Graph it. Done with that. Now, in order to save myself some time, what I might do is test for symmetry. So if it's symmetrical with respect to, I don't know, this polar axis right here, and I know it's symmetrical, then I might only graph the points between 0 and pi, or 180. That way I don't have to spend my time graphing or plotting these points down here because I already know it's symmetrical. So what are some tests for symmetry? They're going to be exactly the same as the ones from the Cartesian plane. So I'm going to test with respect to the x and y axes and the origin. Now the only difference is they're called something different. Here this is the, I guess what would this be called? I don't know. I think it's called the. We'll just call it the polar axis. I think this is called the polar axis. So I'm going to test with symmetry in respect to the polar axis. So what am I going to do? I'm going to, instead of testing positive and minus y, I'm going to test positive and minus theta. So down here, below here, the only difference between, if it was symmetrical between these two things, is here theta would be negative and here theta would be positive. So for testing respect to polar axis, or the x, it's just easier to think of it that way. So most of the time I'm going to be using the Cartesian plane. I'm just going to replace theta with minus theta. So that's one. So now if I want to test with respect to the y-axis, or in this case this isn't called the y-axis because it's a circle, so there is only one axis. So this is just the line pi over 2. Or I can think of it as the y-axis. So if I want to test with respect to this, what I'm going to do is have theta replaced with pi minus theta. So I've got a theta over here. This would be, or I've got some theta, pi minus theta, so that's pi minus theta is over on this side. I've got theta. So that tests for one side to the other of this line. So that's that. And one more, I guess, with respect to the origin. So if I had something, I guess it's kind of weird to think of it because it's a circle, but say if I had something, I don't know, weird like this. This isn't symmetrical with the y-axis or pi over 2 or the polar axis, but it is symmetrical. Let's pretend it was an actual shape, but it would be symmetrical with respect to the origin. So to test for symmetry with the origin, I replace r with minus r. So that's all I gotta do. So let me just delete all that crap. Origin r with minus r. So let me just do something simple. I'll graph it, and then this will be the last time I ever graph one of these things until the world ends. So what did I pick out? I mean, I already did all this crap ahead of time, so I didn't feel like wasting a bunch of time on this nonsense. R is equal to, what is it, 1 minus sine theta? Yeah. So before I start wasting my time plotting points, I mean, it just really depends. I mean, sometimes it might just be easier just to plot garbage and then just to see what it says. But let's just go ahead and use the symmetry test. So we'll do the first one, which is symmetry with respect to the polar axis or the x. So this axis right here. I don't know if anyone can see this, but yeah, this axis, x-axis. Replace theta with minus theta. So I don't need to put theta in there. It's already there. So what I'm going to do, just replace this with minus theta, and then sine of minus theta is minus sine, so it's going to change the side. R is equal to plus sine theta. So what this means is that the test was inconclusive. I guess I forgot to discuss that. Well, let me just talk about the results now. If it's not equal, that means the test is inconclusive. If it is equal, that means it is symmetrical. Now, it's kind of weird that it's inconclusive, but there are going to be situations where it doesn't show symmetry in the test, but it is actually symmetrical. But if the test is positive, then it's definitely symmetrical. I don't know, it's like, a pregnancy test or something like that. You may test yourself for pregnancy, and it may come up negative. It does not necessarily mean that it's not negative. But if it comes up positive, then it's definitely a positive. So it's just like that. I mean, that's probably a stupid example, but that's probably the only one I could really think of. But, yeah, so this is inconclusive. So let's go on to the next one then. So, next one, line pi over 2, yeah. So I've got to replace theta with pi minus theta. Oh, well, gotta put the minus sign in there, don't I? Okay. So here I'm going to have to use some of those good old sine formulas. Which one was it? I couldn't even remember what I had to do the distance formula again for it, but I'm not going to do that here. It just takes too long to recalculate it from the distance formula. But I don't remember any of these things. So what did I put it as? Oh yeah, there it is. Now this is going to take up way more room than that. Sine alpha minus beta, these old things. And these will come up frequently when graphing stuff like this. I mean, if you're going to bother to even invest any time on learning these kind of things. I mean, it's good to know how it works, but it's really not worth investing any time in, to be honest. Cosine beta. Ah, damn it. Sine beta. Okay. So now I've just got to plug this stuff into there and then see what happens. So r is equal to 1 minus, and then I'm just going to replace this whole thing. Sine alpha, which is pi, cosine beta, which is not minus theta. I ignore this minus sign because it's already taken into account in the formula. So I don't want to put minus theta, that would be wrong. So that's something to easily forget. I'll probably do it sometimes. Cosine, remember, just theta. They have a different formula for alpha plus beta. Sometimes it's easy to forget that sometimes, especially if one isn't using these formulas all the time. It's just a reminder. It's cosine alpha, which is pi, and then sine beta, which is just theta. Now I'm just going to simplify this stuff. 1 sine theta, that's 0, right? Yeah, so that's 0. Cosine, that's minus, so minus 1. So I haven't done any of this crap for a long time. I always just forget. I always have to just resolve it out by hand. So yeah, this just makes positive, so r is equal to 1 minus sine theta. And this is exactly the same as this. So that means it's definitely symmetrical to pi over 2. So it'll be symmetrical to this like y-axis, even though it's not a y-axis. So that means we got the origin, that's easy. Just r with, replace r with minus r. So that'll be an easy one to do. So I'll just do it down here. So I put in minus r. And obviously it's an inconclusive test because I just multiply the other side by minus 1. So I get sine theta minus 1 instead. These just switch. So the only conclusive bit of symmetry I've found is that it's symmetrical to pi over 2. So let me go back up to this graph over here. And I'm just going to put the points that I plotted earlier. I'm just not going to spend the time calculating all these stuff. I mean, everyone knows how to just plug in an angle and get a point or whatever. So what did I put in? I just did all the easy angles minus pi over 2, and ended up being, what's that? Can't see this. 2 minus pi over 3 is equal to, I rounded it to 1.9 minus pi over 6 equal to 3 over 2. 0 was equal to 1. Pi over 6 is equal to 0.13. This is a mess. Oops. Pi over 3. Oh, I looked at the wrong one. I knew something was wrong. I was going to say, that's just 30 degrees. I knew that one. Didn't even need to calculate that garbage. Okay. So I got these points now. Let me change the scale. It's going to be too small otherwise. Okay, so I'll just kind of double it. I'll say, or how many do I got? I got 1, 2, 3, 4, 5. Okay, so I'll just say 1, 2, 3 of these is 1, 1, 2, 3. So this is 2. So it'll actually be a little bit visible. And this garbage is in. Man, this garbage is in stupid degrees. Oh well. Minus pi over 2 was 2. So what did I say? Here's 2. Make sure that I try to make it a different color. That's hard to see. Look at this blue. So there's 1. Actually, I'll do these other ones over here first, so I can just get rid of them. So pi over 2, that's here. That was 0. Pi over 3 was right here. That's 1.3, so that's like 1 and the third. Make sure I line it up right. So it's like there or something. Oh no, that's 0.13. What am I talking about? So that's like all the way. So here, pi over 3. So that's like, damn, that's like right. That's like right there. Yeah, that's like nothing. And pi over 6. So what's that, like 30 degrees? This is, yeah, 60 degrees, so that's like 30 degrees. It's 1/2, so that's, and I don't like this stupid scale. That's a third, so it's like, right there. Man, I did this stupidly. Oh well. And then 0 is equal to 1, so that's right there. Minus pi over 6 and negative 30 degrees, that's 1.5, so it's probably like, I don't know, here somewhere. Yeah, so it's like right here. Then I got minus 60 degrees, that's 1.9, so it's close to 2, which is 60. So it's like there. Now let's connect this stuff. Ugh. This is going to be terrible. But as you can see, I've saved myself some time because the other half is going to be symmetrical, so it's going to be, you know, I'm not even going to bother plotting the points, but it's going to look like this. Ugh. Started out well. So yeah, it's gonna look something like this. So this shape is called a cardioid because it looks like a heart. And I'm not sure who came up with this shape that's supposed to look like a heart, because, you know, a heart probably looks like this. Like, I don't know, it's like this, and then there's some gross looking like vessel things like up here. And it pumps blood out all over the place. But yeah, that's how to graph. It's you know, I don't recommend to spend much time learning how to do this. It's just I mean, you know, unless you're good at drawing, it's just annoying. And yeah, it's easily done by computers, so it's not really much to look at here. It's just plotting points, and then if you care to save yourself some time, then go ahead and use the symmetry tests. But like I said, it's just only very useful in times where no calculators and computers exist.